Alright guys, this is kind of weird for me too. It's the first video that I've made, so y'all are the guinea pigs. But what we need to talk about is we need to talk about getting into these combination circuits. Now we've been through the series, we've been through the parallel, and we need to make sure that we understand that, because that's the basis of everything else to come. Combination circuits are nothing more than just combinations of series and parallel circuits. So you got to understand the individuals by themselves. The series circuit, you got to know. I mean, without even thinking about it at this point, you have to know a series circuit. First of all, is one path for current, and then all the components are in that same path. You have to know that. I mean, straight up, and recognize what we're dealing with is components in one path. Well, if we only have one path for current, there can only be one current flow. That's why in series, current stays the same. Now, this little bit of information right here, current being the same in series, is going to help you find out how to determine current through other components. If you know one component is in series with another component and you know the current with that other component, well, you can determine the current through that other one, because current stays the same in series. You gotta lock that in. And you gotta realize that if I got a voltage applied, that each individual voltage is gonna add up to that total voltage that I applied. That you have to know. And then how to find resistance in this particular type. Series, you just add them up. It's this value and then this value, it's all in the same path. And in this value, so you just add the resistors up. Now, parallel, you gotta lock in on that too. Parallel circuits, well, that's more than one path. And look, I'm gonna tell you something. You don't see a single junction point in this series circuit, but over here in parallel, we've got junction points. That's how you identify if something is in parallel, because junction points connect two different paths for current flow. And see, and that's the deal. A series is only one path for current. Parallel is more than one path for current. Not just two, but it's more than one. And so if I have more than one path, I'm gonna have more than one current. One path, one current. More than one path, more than one current. You gotta lock in on that. You have to understand that without thinking. Current divides. As simple as that. You got more than one path. Any current that comes into this junction point right here is going to split. Some of it's going that way and some of it's going that way. And guess what? When it does come out the other end, it's going to be the same current that went in. So these two currents will always add back up to the same current that went into the circuit. You got to look at it like this. You have to understand what we're talking about. If you don't understand parallel and you don't understand series, well, you're not going to understand combination circuits. It's as simple as that. So you have to understand series and you have to understand parallel. And it's got to be like that, guys. It can't be just, no, I think I understand it, but I really don't. It's got to be yours. And then last, you got to find total resistance in a combination circuit, in a parallel circuit. And the parallel circuit, you use the 1/over formula, because we're not adding resistances, we're actually adding the conductivity of each one of these paths that we have here. So we invert the resistance value to find the conductivity. So we're really just adding up all the individual abilities to allow current, and then at the very end we're going to 1/over it back into resistance. So in parallel we add up resistors the 1/over way. In series we add them up the regular way. You got to know this. I mean, straight up know this. All right. Now, the way I'm doing these things is I'm not going to wait for you to copy the notes. What you need to do is press pause and then copy the stuff that's on the board and then hit play in a minute because I'm fixing to erase it. All right, here we go. Alright, here's the next thing. The next big thing when it comes to combination circuits is understanding what equivalent resistance is. Equivalent resistance. Well, we've been dealing with equivalent resistance all along. We actually called it total resistance. It's just the accumulation of all the resistances together. Well, in series, it was easy. You just add them all up. In parallel, you just add them all up the one over way, but not so much in combination circuits because we have to do to the type of connection what's required. In other words, if I have two components that are in series, I got to add them up regular, but if those two components are in parallel, I have to add them up in parallel, the one over way. So an equivalent resistance is just a subtotal of resistance as we work through the circuit itself. So focus in on the equivalent resistances, and what I'm going to do is I'm going to show you a method to redraw these circuits so they make more sense, so you understand what you're doing. All right, so an equivalent resistance. That Alright, so let me show you how we're going to use equivalent resistance in a circuit. So this is an example of a combination circuit. You have a combination circuit, got a source, so with this circuit, I'm not even going to put any resistance values up there because you need to understand how we're going to use these equivalent resistances, and then we'll worry about finding how to determine what they are. So what we want to look at is the circuit overall. Now you got to trace the path. I mean, you got to look at it from the side of the source, and I always use the negative side. You can go the positive side, but current flows from the negative toward the positive, so I want to follow the path because the path is everything. So I'm coming out of the source. Now, how many paths are connected to this source? Well, there's one. There's one line. That's what a path is. It's a line on the board. So I got one path that connects, and the first thing I get to is a junction point. Well, junction points ought to tell you straight up that, oop, I'm looking at a parallel connection, because only parallel connections have junction points that have more than one path splitting off of them. So sure enough, that's what I got. I get here and I got a parallel connection that comes back to this junction point here. So I got this resistance in parallel with R2. And then what happens? Well, at that junction point, I'm moving along, and the next thing I get to is a resistor. Not another junction point, a resistor. So the current that comes out of the source, even though it splits, it still comes back together at this junction point to be flowing through R3. And then that current that flows through R3, what does it do? Next thing it gets to is a junction point. At this point, we know current's going to split, and it does. It splits through 4 and 5, comes back together, and comes back to the source. All right, so how do we find voltages and currents and resistances? Well, the main thing we're worried about is finding the resistance value. That's the first thing, because without resistance, we can't find current. So what we're looking at is the first thing we get to is we get to R1 and R2. That is going to be my first equivalent resistance that I'm going to find. I need to find that. So what I'm going to do is I'm going to take and combine the resistances of R1 and R2. And of course, we said they were in parallel. So in order to combine them, you know that's the 1 over X formula in order to do that. And that gives us our first equivalent resistance. So look, we're going to take this and we're going to turn it into REQ, equivalent resistance. Now remember, this one resistance is what we got when we 1 over 1 and 1 over 2 and add them together. This value becomes our equivalent resistance, and that's REQ number 1. Okay? And so that's what we have. Now look, if I'm looking at this and I'm finding this path as it comes around, goes through REQ. Now remember, yeah, it split, but it still all went through the equivalent resistance of those two that we put in parallel, and in that current, it comes and goes right through R3. And so if we look at REQ1 and R3, we can tell that those two values in the same path have got to be in series. Well, we'll deal with that in a second. Let's keep going around and see what we can find. So the next one we find is R4 and R5. We find a junction point. That's another parallel circuit. So we're going to 1 over X to find these values, the equivalent value of R4 and R5 as well. So we're going to 1 over R4 plus 1 over R5 equals 1 over, and that gives us our equivalent resistance for 4 and 5 that we'll call REQ2. Alright, so now I combine 4 and 5 in parallel to create REQ2, combined 1 and 2 in parallel to create REQ1. Now look at the circuit. It's a simple series circuit with 3 resistances. How would I find total resistance? Well, series, you add them up together. So I'm going to take the equivalent resistance, not the resistance of 1, not the resistance of 2. I'm going to take the equivalent resistance, add it to the resistance of R3, and turn around and add in the value of equivalent number 2. Not the value of 4, not the value of 5, but the equivalent resistance, because that's what's in series with R3. Alright, Now, after we do that, we're going to find current, right? After we find and add these three resistance values up, I'm going to come up with total resistance. Well, if I know total voltage and I know total resistance, I can turn around and find total current. That's Ohm's law. So now look, that total current in and out of the source. In every circuit, IT is guaranteed in and out of that source. Source produces all the current. Total current, that's all of it. It produced by the source, it's going to spit out guaranteed to find total current. So total current is flowing through equivalent resistance number 1. But look, it's also flowing through resistance number 3, and it's also flowing through equivalent resistance number 2. And just like in series, I can take my total current, multiply, look, it's Ohm's law, folks. I can take my current, multiply it times my resistance. I don't care if this is an equivalent resistance. Yeah, I'm not going to get the voltage or the current. I'm going to get the voltage across the equivalent resistance, and that's it. Okay? But then I'm going to show you something. So here's the deal. I'm going to take, multiply, and that's going to give me the voltage across there. And then that same current, total current, it's flowing through R3. So you know what? I can go write current for R3 is the total current being the same. And then you know what? I can find the voltage across R3. And you know what else? I got current flow through R2. I can turn around, or the equivalent resistance of R2, equivalent to, I can turn around and find the voltage across it. And look, if I know the voltage across REQ1, you know what I know? Since REQ1 is since REQ is R1 and R2, and I know the voltage across the equivalent resistance, I know the voltage across R1 and R2. R1 and R2 are my equivalent resistance. So if I know the voltage across the equivalent, and look, I multiplied the current times the equivalent resistance, got the voltage for 1 and 2. Now that I know the voltage for 1 and the voltage for 2, I can turn around, using Ohm's law, find the currents through 1 and 2. I already know the voltage across 3. You had REQ2, I can do it the same way as I did REQ1. I can take that total current, multiply it times the equivalent resistance, find the voltage across that equivalent resistance, which we know consists of R4 and R5. And so once I know the voltage across the equivalent resistance, I now know the voltage across 4 and 5. So now I can turn around and find the current. The voltage divided by resistance will give you how that current splits. Now, the next thing you need to lock in, look, if you got to listen to this video 19 times before this stuff sinks in, you need to listen to it 19 times. But the bottom line is, all right, I can't add up, in a combination circuit, I can't add up all my voltages to get total voltage like I do in series, because if I add this one and add this one, those are the same anyway. I'm getting an incorrect representation of my voltage. If I add this one and this one, they're the same, I'm not going to get it. Can't add up all my currents in parallel either, because this current is this current and that current. This current is that current. This current and that current is that current together. So I'm getting the whole tons of current. Well, here's the deal. You can't add up your voltages, you can't add up your currents. But in combination circuits, in any circuit, look, this thing is actually called a power supply. It supplies power in the form of a voltage, potential, and current. Now, Spiewak taught y'all about power when it came to transformers. And the same thing holds true. The amount of power that's produced is consumed by the circuit. Can't help it. It's going to be there. All your powers will add up. So remember, Watt's law is power in the relationship of voltage and current. So after I have all my individual voltage drops, all my individual currents, I can turn around and find all my individual powers. And if I take total voltage times total current, I'll get total power. And the deal is, all your individual powers, where I multiplied my current times my voltage, VR1 times IR1, VR2 times IR2, VR3 to so on and so forth. When I multiply and get all those individual powers, when I add them back up, they should equal the total power applied. So with total voltage and total current, I can determine my total power after finding the individual voltages and currents, VR1, VR2, R1, R2. I can find my individual powers, PR1, PR2, add all my powers up, and that should be equal to total power. This is how y'all are going to check to see if you've analyzed these circuits properly, because you can't add up voltages, you can't add up current, you got to add up power. Okay? So, that thought, we're going to do a circuit here in a minute, okay? Y'all watch this video about 95 times.